So in Chapter 11, we're going to continue our discussion of chemical bonding, and we're going to look at how we can predict the shapes of molecules, and that'll be something called VSEPR theory. And then we'll look at two more advanced bonding theories. Section 11.1 is not currently in my slides. The old example in the previous textbooks was about artificial sweeteners. The new one is about morphine and endorphins. Very interesting, but I didn't have time to make slides on that, and I'm not going to test you on it anyway. So the lesson from that is being able to predict molecular shapes is very, very practical and allows us to develop cool stuff. End of story. So VSEPR theory, how do we figure out the shapes of molecules? VSEPR stands for valence shell electron pair repulsion. And you can't actually say VSEPR as a word, but we get close and call it VSEPR theory. This is based on the idea that electron groups repel one another. It's a very simple model for molecular shapes. It works really well with Lewis theory. So what do we mean by an electron group? And this is very important and often misunderstood by students. An electron group is a lone pair, a single bond, a double bond, a triple bond, or a single electron. Any of those counts as one electron group. These are not electron pairs, they're groups. Now, some of the groups are 2 electrons, some are 4, some are 6. You could even have a group of 1 electron. But a triple bond is one group. A double bond is one group. Any questions on that? So the idea here is that repulsions between electron groups on one of the atoms on the inside of the molecule is going to determine the geometry. Yeah?
I guess why? Why is a single electron? It's so different.
Well, that would be in a free radical.
Oh.
Yeah. So that would be an electron that isn't paired.
Right.
We're really not going to run into those when we predict shapes.
Why is it a group?
Well, because what else are we going to call these?
Oh. Okay.
Yeah.
It's everything that you could ever possibly.
Yeah, it's all the possibilities, and the best word was group. So, yeah, it isn't really a group. How do you have a group of 1? But yeah, it's a good point. So the idea here, here we have our central atom, and if we have electron groups, say this is a single bond between these 2 atoms, here's a single bond, and here's another single bond. This electron pair in this single bond is going to repel the other electron pairs, which makes sense because electrons are negatively charged. We do have to get around the fact that those 2 electrons are a pair to start with, right? But that's because their spins are opposite, and so we're okay with it. But this group is going to repel this group. So if you think about 3 groups around this central atom, how do they get far away from each other? Well, they spread out in space, right? Here, the farthest the 3 groups can get away is an angle of 120 degrees. So what we're going to look at is the different geometries from the different numbers of groups that we might see on the central atoms. And you should have heard of this in Chem 3A. So the preferred geometry has a maximum separation. Maximum separation is minimum energy. So let's look at what happens with 2 electron groups. This will give us a linear geometry. So let's draw the Lewis structure for beryllium chloride. So we'll put beryllium in the middle and put a chlorine on each side. And then we have to count up the number of valence electrons. How many valence electrons does beryllium have? 2. I'll do that right here. 2, and then there's 2 chlorines, and they each have 7. So that's what 16 valence electrons. So we already have 4 for the bonds. 6, 8, 10, 12, 14, 16. And we look at that and we say, well, that violates the octet rule. But that's beryllium in the middle. Is it okay for beryllium to have less than an octet? Yeah, it probably is. The way we tell is we're going to look at the formal charges. So if I look at formal charge on this chlorine, if I break up this molecule by cutting all the bonds in half, this chlorine would leave with 7 electrons. There's 2, 4, 6, and we get 1 from the bond, 7. Chlorine came in with 7, it leaves with 7, that's 0 formal charge. The other chlorine, exactly the same situation. This beryllium would leave with 1 electron here and 1 here. It came with 2, it leaves with 2. So 0 formal charges. Beryllium is something that can do these exceptions, so this is good. This is fine. So VSEPR theory is based on looking at a Lewis structure. So we look at the Lewis structure and we ask ourselves, well, how many groups of electrons are around the central atom? 2. We have 2 single bonds. Each single bond is considered a group. So we have 2 things that are trying to get away from each other. And so they're going to be on opposite sides of that central atom. I kind of think of these 2 groups as maybe this is you and this is the worst ex you've ever had, right? You hate the person, just detest them. This is the earth. You are on one side and that person is on the other side of the earth. That's as far away as you could get, right? That makes sense? So they're going to get away from each other. 2 groups getting away from each other is going to have an angle here of 180 degrees. That's the farthest away they can get. That's the minimum energy, so it's more stable. So then we look at how this lines up, and it's a line. And so we call this a linear geometry. All the atoms are in a line. Linear seems to make sense. And this is confirmed by observation. Any questions? Let's look at CO2. Yeah, computer issues. There we go. So draw the Lewis structure for CO2. And I'm going to draw these Lewis structures fairly quickly because we already covered that. So 2 times 6 valence electrons plus 4, 16 again. So 2, 4, 6, 8, 10, 12, 14, 16. This is just like beryllium chloride, but with the letters are different. Is this okay? Does carbon put up with a less than an octet? No, carbon is really going to go for the octet. So this is not one of the exception ones. This is a regular one. So the carbon doesn't have an octet. That means we need to share more. So I'm going to take a pair of electrons from this oxygen and share. That oxygen still has an octet, and now the carbon has 6 electrons, which is better. But the other oxygen needs to pitch in and share also. We end up with that. So then to look at the geometry, we look at that central atom and ask ourselves, how many groups? 2. A double bond is a group. This double bond is a group. So 2 groups again. They're going to do the same thing. They're going to be on opposite sides of the central atom. The double bond contains 4 electrons, but it's a single group. Because these are shared between the same 2 atoms, they can't move away from each other. They're stuck between those atoms. So we have linear geometry with an angle of 180 degrees again. So this VSEPR theory is very visual. It can even be tactile. I'm going to have balloons, and we've got models, and everybody can get this. So if if you can look at a Lewis structure, you don't even have to be able to draw the Lewis structure. I mean, you should be able to do that. But if I give you the Lewis structure, everybody can learn how to do the shapes. Okay? So if I'm losing you at some point, stop me and ask for clarification. Okay? Yeah.
So is it because of the number of bonds that carbon likes to form that we give it an octet? Or how do we know
the octet rule applies in general.
Right.
So we go with the octet rule. That first example, we didn't because beryllium and boron are the two elements that often have an incomplete octet.
Oh, it's one of the exceptions.
That's one of the exceptions, right? Carbon is not one of the exceptions.
2 and 3? 2 and 3?
Well, it's just that they're so small. The other thing to do is to look at formal charges. So if we look at the formal charge here, they're all going to be 0.
Right.
If we go back to 2 here and 2 there, we're going to have formal charges.
Okay,
Yeah. So try to do octet rule first.
right.
Then look at the formal charges. And if the formal charges aren't 0, see if it's possibly one of the exceptions.
So the reason that this has 2 electron groups, even though they're double bonds, is because they're sharing the electrons and those 2 can't.
Right. They can't get away from each other. So this is actually a model of CO2. And here's the double bond. The double bond, there's 4 electrons, but it's between the carbon and the oxygen, and they can't move away from each other. Right? They're stuck.
So then we just consider it
One group.
one group of the double bonds is 1 electron group, and the other one's the other.
Yeah, the one double bond is one group, and the other double bond is one group. Yeah, I don't want to get hate mail. Yeah. Okay, so 3 electron groups. Let's draw the Lewis structure for BF3. So boron and 3 fluorines. And then we count up electrons. Boron has 3 valence electrons. And there are 3 fluorines, and they each have 7. So I believe that's 24. And then we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So I throw all the electrons around. Should I make a double bond to give boron an octet? Could boron be an exception? It could be an exception. So let's check the formal charge. So boron brings in 3 electrons, and if I cut these bonds in half, split them equally, boron leaves with 1 electron, 2 electrons, 3 electrons, 0 formal charge. And the same thing with the fluorines. They brought in 7, and they're going to leave with 7. So this is another one of those exceptions to the octet rule. And again, formal charges help us to decide whether that's appropriate or not. So, looking at the boron, how many groups? 3 groups, right? How can 3 things separate around a central point? Well, they would fall in a plane because 3 points define a plane, and the maximum separation they can get is 120 degrees. And that shape, if we connect the fluorines, that shape makes a triangle, right? It's a triangle, and it's in a plane, it's flat. So we call it trigonal planar, because there's some other triangle things that aren't flat. So trigonal planar. Now, some of these names might be a little hard to remember exactly how they're spelled, exactly how they're pronounced. But most of this on the next exam will be multiple choice. I'm not going to ask you to come up with trigonal planar from nothing. It would be in a list, and you have to pick the correct one, okay? Here's formaldehyde. I don't expect you to know its name. Here's the Lewis structure. We actually drew that in the previous chapter. Looking at this Lewis structure, here's the carbon. How many groups? 3. 1, 2, 3. Single bond is one group. The other single bond, one group. The double bond, one group. So 3 groups. 3 groups are going to spread out in a triangle, right? Well, this does make a triangle, but now the things that are spreading out aren't exactly the same, right? The oxygen is bigger than the hydrogens, and there's a double bond here, and so the oxygen is going to push the hydrogens a little further away, and the hydrogens are like, well, you're less offensive than that guy, so I'll get a little closer to you. But the bond angles are very close to 120, and this is still a trigonal planar geometry. Yes?
How are we going to find the angles?
How are you going to find the angles? That's an excellent question. I would expect you on this to be able to say that this bond angle is larger than 120 and this one is smaller. That's it. Because the exact amount really doesn't matter. And you would know that these are bigger. This angle is a little bigger and this is a little smaller because double bonds take up more space and because this oxygen atom is bigger than the hydrogen atoms. And we'll talk a little bit more about that as we go along. Yeah, so for the previous one, this one is 120 because these are identical things. It's 3 identical things. A circle is 360 degrees. You divide it by 3, you get 120. Yeah. So let's look at a conceptual question. A central atom in a 3-atom molecule forms 2 double bonds and has no lone pairs. What is the geometry of the molecule? Some of us might need a picture. Others might be able to do it just from the words. So the possibilities are trigonal planar, linear, or not enough information is given to determine the geometry of the molecule. To solve the problem, it is necessary to know how many electron pairs are in the other 2 atoms. Linear. So the key here is 2 bonds. It's got 2 double bonds. That's 2 groups. There's nothing else going on. It says there's no lone pairs or anything. 2 groups, opposite sides, linear. It might be helpful to draw a picture. So there's my central atom. And here's this atom, and it's got a double bond, kind of making it look like a model. And then the other double bond over here. And we see that this is one group and this is one group. Now we could draw it lots of different ways, but 2 groups are going to get on opposite sides. So answer is linear. Any questions? Well, what about 4 electron groups? This is where things become a little harder to visualize because now we're 3-dimensional and not 2-dimensional. So this is where balloons can be very helpful. So here we're looking at 2 balloons, and if you tie them together, they will naturally move away from each other. If you put a 3rd balloon in there, it'll squeeze those 2 closer together and make this trigonal planar geometry. So when we add that 4th balloon, we get this tetrahedral geometry. And here is the geometric shape, tetrahedron. It's a 4-sided thing, right? And we don't run into tetrahedrons very often. You could also call it a trigonal pyramid in a way. It's a pyramid that has a triangle at the base, right? But we call it a tetrahedron. The bond angles here are 109.5 degrees. So just memorize that one. I took geometry in high school. That was before most of you were born. And I honestly don't remember how you would divide 3-dimensional space into 4 sections. I don't remember how to do that, but I know the answer is 109.5 degrees. So there it is. That's a tetrahedron. So if we look at a molecule like methane, and here is its Lewis structure. It's very simple. There aren't any lone pairs on this one. We draw it like this. We use top and bottom, right and left, because that's convenient on a piece of paper or on a screen. We look at the carbon here in the center and ask ourselves, well, how many electron groups are there? Well, there's 4 single bonds. Each single bond is an electron group, right? So 4 bonds. How do 4 balloons get away from each other? They make a tetrahedron. So this is a ball and stick model of a tetrahedron. These are harder to draw because they're 3-dimensional and we have to represent that somehow. The angle in the Lewis structure here is 90 degrees. The angle in the tetrahedron is 109.5 degrees. They're going for maximum separation. They repel each other. So this is not flat. It's a tetrahedral geometry. And, the prefix tetra means 4. 4 groups, tetrahedral. Any questions? Okay, so let's test our knowledge. What is the geometry of the HCN molecule? This is the Lewis structure. So this is the central atom, right? How many groups?
2.
I heard 2 and I heard 4.
It's 2.
There's 2. So the triple bond, we're tempted to say, well, that's 3 groups. It is 3 pairs of electrons, but a group is not necessarily a pair. It's a group, okay? So this is one group. They can't separate because they're stuck between carbon and nitrogen, right? This is the other group. 2 groups, doesn't matter what they are. 2 groups, opposite sides. What's the geometry? Linear. Any questions about that? What if we have 5 electron groups? Well, here's an illustration of 5 balloons. So this makes a shape called a trigonal bipyramid because it is 2 triangular pyramids put together. So that's where the bipyramid comes in. So here we do not have equal angles because you can't divide 3-dimensional space into 5 sections. It doesn't work. So what we have here is we have 2 balloons that are opposite each other, and then we have 3 balloons around the middle. And so the angle between these balloons will be 90 degrees, and the angle between these balloons will be 120 degrees. Sometimes it's easier to look at it this way. And so I imagine that this is this little girl. Oh, there's her bangs. And there's her body. She's like on point or something. And this is her tutu spinning out around her, right? We got that picture? Make it go away because I covered up the model. So these are equatorial. I'm sorry, these are axial, like the North Pole and the South Pole. This is the axis. And then these are around the middle, around the equator. So these 3 form a trigonal planar structure in the middle, and their angles are 120. And then these 2 are 90 degrees. So not all the angles are the same. Any questions about that? Yeah, you're going to memorize that.
Wait, which 2 are 90?
This angle is 90, and this angle from this one to this one is 90.
Okay, between each chlorine?
Well, they're all chlorines is the problem.
Yeah. Oh, yeah.
So this is 90,
Between
and
that.
this is 90.
Yeah.
Because they're on opposite sides, and so 180.
Then the trigonal planar. and
Yeah, it's the
trigonal-
guys in the middle. The 2 is the 120 degrees. So there's 120, and between these 2 is 120 and these guys. Okay? Yeah, it's one of those things that you need to see a three-dimensional object so that you can get a picture in your head. I don't know about you, but for me, once I get the picture in my head, I'm good, because I can bring that up anytime I want, right? This is a model, ball and stick model, like the one shown in the picture there. And the purple bonds are the axial positions, and the gray ones are the equatorial. And you see the angle here is 120, the angle here is 90. Right? And model kits are great, and if you're going to take OChem, go ahead and buy a model kit right now so you can use it. But if not, even gumdrops or marshmallows or toothpicks, little bits of clay, you can make these things at home. Personally, I like the gumdrops because then, when you're done studying, you can eat them. Right? This is a molecule that would have this structure. Here's its Lewis structure, and as we look at it, this is one that violates the octet rule, right? Because phosphorus is in period 3, so it's a big guy, it can do that. And we see that there are 5 groups around the central atom. Well, what about 6 groups? Where is this going to stop? It's going to stop with 6 groups. So this shape is called octahedral. This shape. So there's the octahedron. It's a square pyramid on top and a square pyramid on the bottom. But it's also an octahedron, and that's shorter than square by pyramid, whatever that would be. SF6 is a molecule that would have this geometry. We look at the sulfur, and it has 6 single bonds. 6 groups get away from each other by making an octahedron. And so you do need to remember that 6 groups give an octahedron. 5 groups is a trigonal bipyramid. But if you can get the image of the balloons in your head, it's really not too hard, right? So there's the octahedron. When we get to the octahedron now, we again have 90-degree angles between everything, right? We can still kind of imagine this as a little girl. I mean, little boys could wear tutus also, but they generally don't. That's her tutu going around. But now the tutu is fuller, and so all the bond angles are 90 degrees. Any questions? Okay, let's do a problem here. Determine the molecular geometry of carbon tetrachloride. This is CCl4, not to be mistaken with CCI4, right? Because if it was 2 carbons and 4 iodines, it would be written C2I4. So it can get a little confusing. So to determine the molecular geometry, we first have to draw the Lewis structure. So carbon and 4 chlorines, a good place to start would be carbon in the center and 4 chlorines around it. And then we would look at how many electrons do we have to deal with. Carbon has 4 valence electrons. We have 4 chlorines. They each have 7. 28 and 4 is 32. Again, feel free to use your calculator to do that math. That's fine. Getting it right is the important thing here. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So here we have a correct Lewis structure. All of the atoms have octets, and if we look at their formal charges, thank you, they're all 0 as well. So this is the starting point. So what's the molecular geometry of this? How many groups? 4 groups. Tetrahedral. 4 groups, 4 balloons, did that funky thing, right? And tetra means 4, right? So this is tetrahedral. 4 electron groups, tetrahedral geometry. Any questions about that? So that can be hard to draw, but because I've had to do it so much, I've learned how to do it. So there's one, and then this one's gonna come off at approximately 109.5, and then there's this one coming out in the front, and then that one going in the back. Tetrahedron.